Bismillahirrahmanirrahim. In this video, we'll learn about balanced binary search trees, right? We already learned about the binary search trees in the previous video. If you have not clear concept about binary search trees, I recommend you to stop here and go to the previous video to understand what are the binary search trees. The binary search trees are, we know that they have at most two children, right? And with the property that the left child of a node has the smaller key value than the parent, and right child of a node has a greater key value than the parent. So that's the basic definition of the binary search trees. The binary search trees are used for to implement the dictionary operations, such as find the minimum value, find the maximum value of successors, and mainly it is used for the searching purpose, right? If the tree is the binary search tree is the balanced binary search tree, it gives the big O of log n. We can search any key element at maximum log n time. But if the tree is not balanced, then there is a problem. It can lead to the different dimension. So let's see if we have some binary search tree, and then let's see let how we can search from that particular BST. So for example, if I have some key values 2, 4, 6, 8, 10, 12, okay, and it is required to have a BST of these key values. So how we can insert these elements into the key value? So we will definitely start with the first key value, that is 2. So the tree is empty, so we will insert 2 as a root node. Then 4, we will compare it with the root. So the 4 is greater than 2, it will go to the right hand side of 2. Okay, then the next key element, that is 6. So 6 is greater than 2, greater than 4, it will go to the right of 4, right? 6. And similarly 8 will go to the right of 6. Then 10 will also go to the right of 8. Why? Because it is greater than 2, greater than 4, greater than 6, greater than 8, and so that's why. And now finally the 12 will go to the right of 10. So this will be the shape of the BST if we have the data elements, such data elements, right? So this is nothing but seems like a linear list, isn't it? Like a linked list. Okay, so if I am interested to find 10 out of this BST, what should I do? Definitely I will be going to the root node and I will compare it. Okay, 10 is greater than 2, so I have to go to the right subtree, and then go to the 4, then 6, then 8, and then I will find 10. And if I am interested to find 12, I have to scan the whole list. So this is nothing but a linear list, like a linked list. And in this worst case, this is the worst case of the binary search tree, this will leads to the big O of n, search time. So if this is order of n, then no need to have the binary search tree. It's better to have the array or a simple linear search methodology. So if we want to have to achieve O of log n to search from the binary search tree, we need to maintain, or we need to have a balanced binary search tree. So what is a balanced binary search tree? Balanced binary search tree is a search tree, binary search tree, that where all the leaf nodes are at the same level, or they maybe differ maximum by 1, right? That's the definition of the balanced binary search tree. If there are different approaches, we call one is called the strictly balanced tree, strict balanced. So if we talk about the strict balanced, then it means all the leaf nodes must be on the same level. But then there is the flexible balanced or the height balanced. Height balanced means the leaf node may be differ with maximum difference of 1. So how we can have the balanced binary search tree? So there are different algorithms that are used to make a BST, the balanced BST. One of them is AVL, right? Another is RB tree, red black trees, right? another one is splay trees, right? The other one is, and one more is B trees, and there are several other algorithms that are used to make the BST, the balanced binary search tree. So in this video we will focus on AVL trees, right? So the AVL trees are height balanced trees. These are good but not the perfect balance tree or the strict balance tree. These are the height balance trees, right? So what do I mean by the height balance tree, or the balance of the height balance tree is, so let's say for example, if I have a BST of some shape like this, um, if I have a binary search tree like this. So let me check whether this is a balanced binary search tree or not, or a AVL tree or not, or a balanced tree or not. So let me just fill some key values here. Let me take it 15, left hand side is 10, and the left is 5. On the right side, let me take is 20, 18, and 22. So let's say, so if this is the let's check whether this is a height balance tree or AVL tree or not. So how we can check whether this is an AVL tree or not? So what's the definition of the AVL tree? Definition of the AVL tree, or in order to check a tree whether it is a balanced it is a AVL tree or not, is if we are interested to find whether the tree is an AVL tree or not, right? So what should we do? We need to check the balance factor. What is a balance factor? Let me call it in short BF. What is this balance factor BF? BF is nothing. You can compute the balance factor of every node. How? You need to check the height of the left subtree, you need to check the height of the right subtree, subtract it, and if the value is either 0, -1 or 1, the value after subtracting the height of the left subtree and the height of the right subtree is either 0, -1 or 1, then we call it a AVL tree or a height balance tree. If the value is other than this allowed value, the set of value or the balance factor values, then the tree is not the AVL tree, right? So how we can check whether this tree is a AVL tree or not? Let's test this one. So how we can check the height of every so let's say for example I am going to check from the root, right? So the root says how we are going to find the balance factor, right, for this node. So what should we do? Find the height of the left subtree. This is the left subtree, right? So what is the height of this left subtree? So how you can find the height of the subtree? Just count the number of edges from root to the leaf node. So root to the leaf node, number of edges are 2. That's the height of the left subtree, minus height of the right subtree, right? So count the longest path from that node to the leaf node. So number of edges 1, 2. So either way this is 2. So that is 2 minus 2, that is 0. So it's perfectly balanced. Fine. It's an AVL tree as per this node. So what we need to check at every node. So for example, if I am interested to find the balance factor of this node, so that is what? Height of the left subtree, that is what? It is 1. Height of the right subtree is not there, so it is 0. 1 minus 0, that is 1, right? And what is the balance factor? Okay, note one more thing here. If you are getting +1, that means the tree is heavier by one more child on the left hand side. If you are getting the -1 value here, it means the tree is heavier with one extra child on the right hand side. So, right? So what is the balance factor of this node? So left subtree, that is 0, right subtree, that is 0. So 0 minus 0, that is 0. That's allowed limit, fine. So similarly, what is the balance factor of this node? So height of the left subtree, that is 1. Height of the right subtree, that is 1. So 1 minus 1, that is 0. Perfect. What is the balance factor of this node? That is again 0 minus 0, that is 0. 0 minus 0, that is 0. So that's how we compute the balance factor of every node. If the balance factor is within this allowed limit, that is 0, -1 or 1, then we call that tree as a balanced tree or an AVL tree, right? Now the question is, why do this balance disturbs, right? So for example, if this is the case, whenever we are going to insert any key value, for example, we inserted 2, right? It was fine. We inserted 4, it was fine until here. So you can check the balance of this node. So the node balance factor of this node is 0 minus 1 is 1, right? Fine. But as we inserted 6, so the balance factor of this node is 0 minus 2, that is -2. That is not allowed. So the balance is out here. Balance is out here before inserting the next value. So in order to make this balance, as we insert a node, we need to check the balance factor and we have to make it balanced, and then we insert the next values. So how to do that? Let's discuss it. So there are several cases if we basically want to make our trees balance or make our tree AVL tree. So there are two broad categories. One is called outside cases. Outside cases. So let's discuss the outside cases. What is outside case? Let's say, for example, if I have some value, I inserted 5 in a tree, so it becomes a root node, fine. Then I inserted 4. It will go to the left of this, right? Check the balance factor. So the balance factor is 1 minus 0, that is fine. Okay, this is 0, that is fine. Now I inserted 3. Now what happens? The balance factor is out for this node. If I check the balance factor of this node, that is what? 0 minus 0, that is 0, okay. Balance factor of this node, that is 1 minus 0, that is 1, okay. The balance factor of this node is 2 minus 0, that is 2, that is not allowed. So the tree is imbalanced at this node, right? So the tree is imbalanced at this node. What should we do? The first thing that we should note here is why this problem happens. This problem happens because we insert key value, right? We insert a key on the left of left, right? We insert a key into left of left. So you can see we inserted a key value, that is 3, in the left of the left subtree. That's why this problem arises. That's why this is the problem. Let me call this problem is a left insertion problem. This problem is because we inserted a key value in the left subtree of the node. That's why the balance of that node is disturbed. So this problem is called left insertion problem. So how we can solve this problem? How we can fix this problem? Since this is the left insertion problem, what we can do? We can rotate this tree like this. Rotate the tree like this. I mean, if the problem is because of the left of left, what you can do is you can rotate the tree into the right hand side, right? Like this. Okay, so if I rotate like this, what will happen? So if I rotate like this, so 4 will become node, 3 is at its place, 5 will come at the right hand side, right? What I did, I just rotated like this. So that is called single rotation. In a single rotation towards right rotation, a single rotation towards the right hand side solves the problem. Now let's check the balance factor. So this is 0 minus 0, perfect. 0 minus 0, 0. 1 minus 1, that is 0. So it's a perfectly balanced now, right? So what actually we did, when the problem arises because of the insertion in the left of the left subtree, that is the LL insertion problem, simply rotate it single time to the right hand side, perform the right rotation and fix the problem. Clear? So okay, so this is called this is the case number one. This is the case number one, that is right rotation. Now let's see, this case number one is obviously inside under the umbrella of the outside cases. Now let's see one more problem. So for example, if I have inserted 5, okay, as a root node, then 7 on the right hand side, obviously, right, and then I inserted 10. That again goes to the right hand side. It was perfectly fine until here, and the problem started when I inserted in the rights of the right subtree. Agree? I inserted 10 on the right side of the right subtree of the node 5, and the balance of 5 is disturbed. So here you can check the balance is 0, okay, the balance is -1, fine, the balance is now 0 minus 2 is -2, that is not allowed. So the balance of this node is disturbed because we inserted in the right of right subtree. So let's call this problem R insertion. We inserted on the right of the right subtree. So how we can fix this problem? Similar to this one, we can rotate like this, right? We can rotate like this. If we rotate like this, what will happen? So 5 will come down, 7 will go up, isn't it? Right? So I just rotated it like this to the left hand side. So I performed the left rotation. Clear? So this problem was because of insertion. We insert a key value, insert key into right of right subtree. Right? So that is the case number 2. Clear? So how we can fix this problem? Using the left rotation. If we insert it into if the right hand side is imbalanced, just perform the left rotation. That's it. Okay, now let's discuss about few more cases. This was very simple. We were inserting in the outside this, okay. So now let's say one more thing, that is called inside cases. Okay, okay, inside cases. Inside cases. Okay, so what happens actually? Let me insert 5. So the tree was empty, 5 is the root node. Then I inserted 2. So obviously 2 is smaller than 5, it will go to the left hand side. Then I inserted 4. 4 is smaller than 5 but greater than 2, it will go to the right of 2. Okay, so this is not the outside case. If it is the outside case, then it should be the out of this one. This is inside case. And why let's check the balance factor. So the balance factor of this node is what? 0 minus 0, that is 0. Okay, balance factor of this node is 0 minus 1, that is -1. Okay, what is the balance factor of this node? That is 2 minus 0, that is 2. That is not allowed. So the tree is imbalanced. Why this becomes the imbalance? Because we inserted to the right side of the left subtree. Do you understand? So what we did actually, we insert a key into right of left subtree. Right? That's why this problem arises. So that's the case number 3. How to fix this problem now? So you cannot fix this directly. I mean, by directly I mean is in a single rotation. So we need to perform double rotation, right? This is not 2 rotations, this is double rotation. What is double rotation? What should I do? First of all, I will rotate it from here because the balance factor actually is disturbed because of this node. So we need to fix this. We will rotate it like this one, then we will rotate it like this one. So if I rotate it this node, what will happen? So this will become 5. If I rotate this, right, rotate this, so 4 will go up and 2 will become this, like this one. So do you understand? So what I did, I just rotated like this, right? So now this becomes a simple case, right? And this is nothing but the a LL case, so what we can do, we can simply perform the right rotation, right? We can perform the right rotation and 4 will go up, 2 will be on the left, 5 will be on the right hand side, right? So we actually solve this problem by performing double rotation. First of all, we rotated this one, then we rotated the whole key from 5. Clear? But then you can solve it directly. So how you can solve it directly? So for example, if this is the scenario, like for example, let me redraw it here, 5, 2, 4. If this is a scenario and you want to fix this directly in order rather than rotating this first and then rotating the whole, what you can do is you can simply replace this 4 with this, move this 4 here and move 5 to the right hand side. What do I mean is move 4 here, make 4 as a root, and then move this 5 to the right hand side, and 2 is at its place. So this solves the problem, right? This is a this is a direct way to perform this double rotation. What is the double rotation? Let me just give you one straightforward way. So for example, if this is A, this is B, and this is C, this is the case, then how you can solve it? You can simply move this C up, right? Move this A to the right hand side, and B is at its place. So this solves the problem directly in the double rotation in single go. Okay, so far we have discussed 3 cases. One more case is there. Let's say for example, we inserted 5 as in an empty tree as a root node, then we got 7 is greater than 5, so it will go to the right hand side of this 5, and then I got 6, so 6 will go to the left of 7, if this is the scenario. So you can see clearly the balance factor is out. This is 0 minus 0 0, this is 1 minus 0, that is 1, okay, but this is 0 minus 2, that is negative 2. So that's not allowed, right? So the balance factor is out here. So if this happens, what you can do? Obviously, first of all, why this problem arises? This problem arises because we insert a key element, right? Insert a key into left of right subtree. Left of right. Is it? So that is the case number 4. So the problem is because we inserted into the left of right subtree, right? LR insertion. Clear? So how we can fix it? We can perform the double rotation again. So what we can do? We first of all we can perform the right rotation, right? First of all rotate it rightwards and then rotate the whole to the left hand side. So left right rotation, you can perform left right rotation in this case. So what do I mean is, first of all perform the right rotation from this node. So 5 is there. If we perform the right rotation at this node, 6 will go up, 7 will go here, right? So I perform the right rotation. Now you can perform the left rotation for the whole tree. So 6 will go up, 5 will go left, and 7 is go up. So perform the left rotation here, right? Clear? So that's, we actually perform LR rotation and the problem is fixed. So again you can do it directly. I mean, if this is the scenario, you can do it directly like in the previous case. So we discussed that. So for example, if you have 5, 6 and 7, what you can do? Not like this. If you have 5, 7 and 6, if you have the case like this, you can directly move this 6 to the 5, right? 6 here and move the 5 to the left. So what you need to do is move 6 up and move 5 to the left, and 7 is at its place. So you can perform this double rotation in single go, right? So far we discussed 4 different cases of making the tree AVL tree. The case number one is the outside case, right? So the outside case was case number 1 happens because of the LN insertion, right? So we need to simply perform the right rotation. This is the case number 1. The case number 2 was because of the right insertion, and we perform the left rotation in a single phase, single rotation. So that's the case number 2 in outside case, right? Then we discussed about the inside cases. Inside case, so the problem was because we insert a key into the right of the left, and that problem, let me call it uh, RL insertion, right? And then what we did, we performed a double rotation here. What we did, first of all, we performed a left rotation, right? And then we performed the right rotation. So left right rotation we performed in order to solve this problem. What we did, the rule number 3. So first we perform the left rotation, then we perform the right rotation in order to fix this problem. And then the case number 4, we just discussed that if this happens because of the insert a key into the left of the right subtree. So if this happens, what we need to do, we need to perform the LR rotation. First of all, perform the left rotation, and then you can rotate the whole values from this one. Right, so these are the 4 rotation rules. Now one important thing we need to note is the rotation always performed within 3 keys, 3 nodes, right? So rotation always performed within 3 nodes, right? So as soon as the balance is disturbed, we will perform the rotations, right? So let's solve one example or do one exercise, and we will know how we can create an AVL tree. Let's do one exercise. So let's say, for example, I have a few key values that I want to insert into into a binary search tree, and I want to make a AVL tree. So for example, I have key values 14, 17, 11, 7, then 53, then 4, then 13. Okay. And if this is the case, then what should we do? What key values are there? And these are the key values. Let's start with the 14. Obviously we don't have any choice. First of all, we get 14, we'll insert into the binary search tree, and we'll make it root node. Then we get 17. 17 is greater than 14, so we'll move it to the right of 14 and we'll insert 17 there. Then we got 11. 11 is smaller than 14, so it will go to the left of 14. Then we get 7. Okay, one important thing, as soon as you insert a node, new node, you need to check the balance factor. So let's check the balance factor. So this is 0, this is 0, so this is 1 minus 1, this is 0. So far it's fine. So now insert 7. 7 is smaller than 14. Let's go to the left hand side. 7 is smaller than 11. Move to the left hand side and insert 7 here. Now you need to check the balance factor. So the balance factor of 7 is 0. Okay, balance factor of 11 is 1 minus 0, that is 1. Okay, balance factor of 17 is 0. Balance factor of 14 is 2 minus 1, that is 1. So that's fine, it's balanced. Now let's insert 53. So 53 is greater than 14, 53 is greater than 17, so it will go to the right of 17. 53 is here. So now let's check the balance. So this is 0, this is 1, this is 0, this is negative 1, so 2 minus 2, this is 0, so perfectly fine. Okay, then we got 4. Now let's insert the balance, the 4 into this tree. So 4 is smaller than 14. Okay, 4 is smaller than 11. Fine. 4 is smaller than 7. So we'll insert in the left hand side of 7. 4 is inserted here. Now let's compute the balance factors. Balance factor of okay, let me write the balance factor of every node. This is 0. This is 0 minus 1 is negative 1. So this is 0, right? This is 1 minus 0, that is 1. Fine. So balance factor of this node, 2 minus 0, that is 2. No, this is not allowed. So the balance is disturbed here. As soon as we insert a new node, we check where the balance is disturbed. So if the balance factor is out, we need to fix it first and then we need to recompute it. So what is this case? This is case number 1, left. This is because of insertion into the left of left subtree, right? So simply we perform a right rotation for here and we can fix this problem. So let's fix this problem. So 14 is there, 17 is at its perfect place, 53 is at its perfect place. We need to rotate it. So if we rotate it like this, what will happen? 7 will come up, right? 11 will go in the right of 7 and 4 is already in the left of 7. Clear? So this is how we are going to fix this. So we just rotated this one. So now let's compute the balance factors. So this is 0, this is 0, this is 1 minus 1, this is 0, fine, this is 0, this is negative 1, fine, this is 2 minus 2, this is 0, that's fine. Now it's an AVL tree. Fine. Okay, now let's insert this key value 13. So 13 is smaller than 14. Fine. 13 is greater than 7. Okay. Go to the right hand side. 13 is greater than 11 as well. So we insert it into the right of 11. 13. Now let's compute the balance factors. Balance factor of 13 is 0. Fine. Balance factor of 11. Okay, let me just write it here. Balance factor of 13 is 0. Balance factor of 11 is 0 minus 1 is negative 1. Balance factor of this 4 is 0. Balance factor of 7, 1 minus 2, that is negative 1. Okay. Balance factor of 53 is 0. Balance factor of 17 is negative 1. Balance factor of 14, 1, 2, 3 minus 2, that is 1. It's fine. That's an AVL tree. Okay, fine. Now let's do one twist. Okay, let's insert 12. One more key value. Let's insert 12. So if I insert 12, so 12 is smaller than 14, it will go to the left hand side. 12 is greater than 7, it will go to the right hand side. 12 is greater than 11, it will go to the right hand side. 12 is smaller than 13, it will go to the left of 13. Right? So now let's check the balance factors again. So the balance factor of 12 is 0. This is not balance factor of 13 is not 0 now. It is 1 minus 0, that is 1. Fine. The balance factor of 11. Balance factor of 11 is now 0 minus 2, that is negative 2. So the balance is disturbed here as we inserted 12. So the balance is disturbed here. So first of all, we need to fix this problem. Then we'll recompute the balance factors for every node again. So the problem is here with this one, right? So how we can fix this? What is this problem? This happens because of we inserted into the left of right subtree, right? So we already discussed this case. So we can fix this easily. Let me do it directly. What you will do, you will move this 12 here, right? And move the 11 to the left hand side, then the problem will be fine. So let me just redraw it. 14 is okay. 17 is on right hand side, 53 is there. Okay, so here 7 is at its place, perfect place. 4 is at its perfect place. The problem was here. So if we fix this problem, so we'll move 12 up. So on the right of 7, that means update this 12. 13 is at its perfect place. So this 11 will go in the left of 12. Remember the rule, we just discussed the rule, right? We'll move 12 up, 11 to the left hand side, 13 is at its perfect place. So now let's compute the balance factor once again. So the balance factor of 11 is 0, okay. Balance factor of 13 is 0, okay. Balance factor of 4 is 0, okay. Balance factor of 53 is 0, okay. Balance factor of 12 is 1 minus 1, 0, okay. Balance factor of 7 is 0 minus, okay. 1 minus 2 is negative 1, okay. Balance factor of 17 is 0 minus 1 is negative 1, okay. Balance factor of 14 is 1, 2, 3 minus 2, that is 1, fine. Now this is an AVL tree. Great. Okay, now let's do one more thing. Let me insert 8. One more key value, that is 8. So 8 is smaller than 14, left. 8 is greater than 7, go to the right. 8 is smaller than 12, go to the left. 8 is smaller than 11, so insert it into the left hand side. insert 8 here. So now let's compute the balance factors again, as we inserted the new node. So the balance factor of 8 is 0. Balance factor of 11 is, now we need to update it. This is 1 minus 0, that is 1. It's not 0. So balance factor of 12 is 2 minus 1, that is 1 now, right? Okay. So the balance factor of 7, that is 0 minus 1, 2, 3, that is 1 minus 1, 2, 3, that is negative 2. So that is not allowed. So the balance is out here at this subtree, right? So the balance is out here. So balance is out here. So how we can fix it? Balance is out with 7. Why the balance is out? Because of this. But the balance is out this. So we will only focus these 3 nodes in order to fix this, right? So the balance is out here. So we'll fix here because of these nodes, this one to the right side, right subtree. So we'll use these 3 nodes in order to fix this. So how we can use this? Simple. So we already know this rule. How we can fix it? Let me just redraw it here, and then we can see. So for example, okay, so 14 is at its fine place, 17 is at its fine place, 53 is fine. Okay, now we need to fix this, right? If we fix this problem, let me move it directly. So what will happen? This 11 will go up, right? 11 will go up. So 11 will become the left child of 14, and then what will happen? 11 will go up, right subtree is fine, so right is 12, that is fine. Okay, that is fine. Then what will happen? What should we do? What should we do? 12 is there, and the left is, okay, so this 7 will go to the, if 11 is moved up, 7 will go to the left, right? And 7 already have a left child, that is 4, right? So what's remaining? So 12 is there, 12's right child is already 13, so that will be there. Okay, see one more time what we did. So from here 14 is this is fine. What we did, the problem was here, so we moved 11 up, so 11 becomes the left child of 14, and 7 will go down, right, as per rule. So 7 comes here, so whatever is with 7, the left child is 4, that is there. So we moved 11 here, 12 is at the right side, 12 is at the right side, whatever is the children of 12 that are with the 12, fine. So what's remaining? The remaining is the left child of 11, that is 8. So where should it go? 11 already have a new left child, that is 7. So what should we do with this 8? Remember, so 8 was as the left subtree, was the left child of 11. It must go in the left subtree of 7, right? So it must go in the left subtree of 11. So but there is already 7 in the left subtree. So what we will do, we will fix this 8, we will make this 8 right child of this 7. Fine. So understand this one more time. What I did, it's very simple. We just moved 11 up. 11 is the root now. So 12 is already on the left hand side, fine. 13 is the child of the 12, that is fine. 7 will become on the left hand side of 11, that is fine. 4 is already on the left subtree of 7, that is fine. 8 was left child of 11. The new left child of 11 is 7. So whatever is the left child of 11 will become the right child of 7. Fine? Okay. Now let me insert one sorry, one more key value there. Okay. Okay, so let's compute the balance factor for this BST. So this is 0, fine, this is 0, 1 minus 1, 0 is fine, this is 0, fine, this is 0 minus 1 is negative 1, that is fine. So this is 2 minus 2, that is 0, fine, this is 0, fine, this is This is 0 minus 1, that is negative 1, fine. This is 1 2 3 1 2 3 3 minus 2, that is 1. That's perfectly fine. So this is the AVL tree. So we understand that if we insert any new key value in a AVL tree or in a BST, after every insertion we need to check the balance factor. If the balance factor is out, we need to fix it. This is the case when we insert any key value in it. Now let's see if I am interested to delete some key value from this binary search tree. Okay, let me delete 53. How we can delete this? So remember, in a binary search tree, how we can delete a key value? Easy. First of all, check whether this is a leaf node or not. If it is a leaf node, simply delete it. Yes, 53 is a leaf node, you can simply delete it. But if it is not a leaf node, then what you need to do? You have to check whether if it only contains one child, right? You can make the child you can attach the child of that node to its parent, and you can delete it. But if it has two children, then you cannot delete it like this. You need to replace it with its successor, and then you need to check whether which case it is. So you can go to the previous video if you are interested to find how to delete an element a node from a binary search tree. So let's delete 53. 53 is a root node. It's very simple. So it will simply delete it. So 14 is there, 17 is there, so 53 is deleted. So 11 is there, 7 is there, 4, and this is 8. Here I have 12 and 13. So now check whether this is a AVL tree or not. So how we can check? We can check with the balance factor. So the balance factor is 0 0 0 0 negative 1 0. This is 0. The balance factor of this node is 1 2 3 minus 1, that is 2. That is not allowed, so it is not an AVL tree. So let's make it an AVL tree. How we can make this AVL tree? So the balance factor is out. Where the balance factor is out here at this node. So what we need to do, we need to rotate from here, right? So balance factor is in the positive side, it means the left side is heavier. So what we need to do, we need to perform a left rotation, right? So if we right rotation. So if we perform a right rotation, what does it mean? If I perform a right rotation, so what will happen, how it will look like? So if I perform a right rotation along these, so obviously we are talking about these three nodes, right? So if I perform a right rotation, so 11 will go up, 14 will go in the left, right? And 17 will go in the in its place, that is the right of 14, right? And what will happen now? Okay, so what will happen now, we rotated it from here. So 11, so the left child of 11 is, left subtree of 11 is there. Left subtree of 11 is what? 7, that is its place. 4, that is its place. 8, that is in its place. Now what's remaining? The remaining is the right subtree of this 11. Right subtree of this 11 is there, but now the new right subtree of 11 is 14. So what we will do, we'll attach this right subtree with the left, at the right hand side, but in the left of 14. So this is 12 and this is 13, right? So what actually we did, simple. So we performed a right rotation, and the new right child of 11 is 14. So whatever is on the right of this 11 will go in the left of this 14. That's the simple rule. So now let's check the balance factor. So this is 0, this is 0, 0. Leaf nodes are always have a balance factor of 0. So this is 0 minus 1, that is negative 1. So this is 0, this is 2 minus 1, that is 1. Okay, this is 2 minus 3, that is 1. Fine. So that's a balanced binary search tree or an AVL tree, right? So you can see the leaves are different at maximum of the 1. That's why we are calling it the height balance tree. Clear? Now you can test it by deleting some other values. So for example, if you delete 7 from this node, what will happen? If you delete 14 from this node, what will happen? So you can try you can practice with the different values. Okay, now one most important thing is, what is the time complexity of building an AVL tree, right? So or searching in an AVL tree. So the time complexity of preparing this AVL tree and searching in the AVL tree is obviously the log of n, right? But since this is the height balance tree, there could be some additional leaf nodes that doesn't come in this one. So the exact value is 1.44 log of n. But when we talk about the big O, we'll always take it log of n, right? So that's how we actually compute the we prepare the AVL tree, and how we compute the time complexity. Now your task, the assignment or the work that you need to do is number one, what do you need to do? You know the logic. What you need to do now, you need to write algo for AVL, right? AVL, both insertion, insert a key, and delete a key from the binary search tree. So you need to write the algorithm for AVLs, right? AVL tree. So that's what you need to do. The number one first task. Number two that you need to do is you need to prove the correctness of the algorithm, right? So you already know that how to prove the correctness. Obviously you are going to perform the dry run, right? Okay, the third task is you need to compute time and space complexity of your algorithm of the AVL, right? Time complexity of AVL trees. So that is your assignment that is due before the next lecture. So you have to submit this as early as possible. Let me just summarize this. We discussed AVL tree in this video. So we discussed that balanced binary search trees are more efficient to use. So in order to make the balanced binary search tree, one approach is AVL tree. In AVL we discussed 4 different rotations, 4 different cases, that why the balance is out from the AVL, right? From a binary search tree. So we discussed the 4 different cases, and whenever you are going to insert a node in a binary search tree, at every insertion or every deletion you are going to compute the balance factor at every node, and whenever the balance factor is disturbed, you need to perform some rotations depending on the case. You need to perform rotations, and then you need to make it balance, right? So that's the simple step for the AVL. Do prepare your assignment and submit it. I hope this is clear. If you have any questions about this topic, just write in the comments, so I will address those questions. Thank you very much.